This one took me so long, but I think I know now. I know how to do it.
Oh, okay. So we're going to do number 8. We've got a spider of very little mass hanging from one of its threads, and it acts like a spring with the spring constant of this. And once the thread's length increases, they want it in meters. So this one I did a force diagram for. So
This is the Y.
the Y for it would be a force diagram, yep. Now don't worry if you can't draw a spring as well as I can, you know.
Alright.
And this is my spider, so I'm just going to label it M for spider. And we have a force gravitation down, otherwise known as the weight, and a force of the spring up. Actually, you know what? I'm going to move those. I'm going to move those to act on the spring rather than on the spider. So the force down is the force of gravity on the spider, and upwards is the force of the spring. And that's my whole force diagram. Okay. So we'll go down to the how. And from my equation sheet, I know that equation. I'm going to start off with the sum of my forces add up to 0, right? And I have two forces. One upwards, force of spring, so I'll put that in as positive. And then one downwards, which is negative, FGS. That equals 0. Oh, I should probably grab this for my equation sheet also. And I can even grab this. Alright, those are all, everything in black is just copied from the equation sheet. Alright? Okay. And I keep in mind that the negative here in my Hooke's law has to do with the fact that the change in length, the delta L, is in the opposite direction as the force. Right? So it doesn't affect the magnitude, it's just the directionality, which I've already taken into account over here. So here I'm just going to go that the force of my spring equals the weight of the spider. Right? And the force of my spring, well, the magnitude of it, remember no vector sign there, is K delta L. Force of my spider would be the mass of the spider times little g because it's on the earth. And they want me to find the delta L. So delta L equals ms g over k. Mass my spider, 0.25 grams. So 0.25 times 10 to the minus third kilograms. So I have to use base units since this is in newtons per kilogram. Over my K, which is given to me 72 newtons per meter. Leaves me with an answer in meters. Alright, so we're going to do number 7 now. We've got the system of electrons and protons having a net charge and a total mass of this. And they ask us to find the number of electrons and the number of protons. So, I think essential in your Y is things like understanding the net charge is caused by the charges without partners. So here there are extra electrons.
And you know that because of the negative.
Oops. Protons.
You know that because of the positive.
Right. Because I think mine's positive, right? Yeah. My net charge is positive, so I know there's extra protons. The other fact I'd probably get in there is each particle carries one quanta of charge. And I mean, I could probably put a line in there that said, like, the mass is due to all of the particles. That might actually be good to have in there. Seems silly, but is caused by all the particles. Alright. Alright. So, really the only equation for this from anywhere is that total charge equals the number of particles times the charge on each one. If you go back to our Y, we said that the charge total or charge net was due to the extra number of protons. So I'm going to call that NPX for extra times the charge on each one, which would be E positive. Okay? The amount of charge would be E, and the type of charge would be positive. And we said that the total mass is due to the mass of the number of electrons plus the mass of the number of protons. Right? Well, the other thing to realize is that the number of protons, not mass, protons. The number of protons is going to equal, remember this is the net charge is due to the protons that didn't have a partner. So the total number of protons would be the total number of electrons plus the number of extra protons. So if you had, 15 protons and 10 electrons, 10 of those protons are going to have a partner, 5 are not, and it's those 5 that would cause the net charge. Okay? So we also would then say, okay, well, the mass total, the net mass, the mass of the electrons would be the number of electrons times the mass of one electron. I'm doing a little m there. Plus, this would be the number of protons times the mass of a single proton. I know it's kind of hard to tell, but there's capital M's and lowercase m's there. All right? And then if you think about things that you know the net charge. You know the charge on a proton. So you can figure out NPX. You know the total mass. You know the mass of an electron. You know the mass of a proton. You can take this and substitute it in here. And that leaves you with only one unknown, which is n sub e. And so you can solve an equation with one unknown. Right? So things to watch out for when doing this. Let's see, Q net is given to me. Oh, they're all given to me in good, nice base units of coulombs and kilograms and everything. So I don't even have to worry about conversion, right? Or I can just plug in. The equation you get here, while it's not that, it's a little tricky. A lot of people are using Wolfram to solve it, rather than going through the algebraic steps.
That wouldn't help us on a test.
Why not?
So how to use
Have you looked? Let's check.